Thank you for the introduction. So yeah, I'm Kanaka Oshiro from Sapian University. First would like to thank the organizers for this opportunity. Thank you very much. And I'd like to talk about minimum numbers of Dehn colors of knots and the symmetric local biquandle cocycle invariants. This is our joint work with Eri Matsudo from Nihon University and Gaishi Yamagishi, who was my master course student. So let me start by the definition of Foxby colorings. So let K be a knot, and D are diagram of K, and let P be a of prime number. Foxby coloring of D is a map from the set of arcs of D to ZP satisfying this condition. So this condition is twice of the color of the over arc is equal to the sum of the colors of under arcs. And the minimum number of Foxby colors of K is denoted like this and defined so like this. So this is the minimum numbers of distinct colors which can be used for non-trivially Foxby color diagrams of K. So let's see this example. When P is equal to 5, these two diagrams are diagrams of 2, 5 torus nodes. And they are colored non-trivially by Fox or 5 colorings, like this. And the difference is this red one is colored with 5 colors, but this right one is colored with 4 colors. So this means the minimum number of Fox 5 colors of this knot is less than or equal to 4. So yeah, like this, we can calculate minimum numbers of Foxby colors. And actually, there are many studies about minimum number of Foxby colors so far. So yeah, I'd like to show the previous studies, previous results here. So when P is a prime number less than or equal to 19, the minimum numbers of Foxby colors are uniquely determined like this. So this means they don't depend on knots. And the last one is shown by Nakamura, Nakanishi, and Sato. So they gave the lower bound of Fox, the minimum number of Foxby colors like this. So lower bound is this is a floor function of log 2p plus 2. And next, Dehn P colorings. Let D be a diagram, and we denote by RD the set of regions of D. Let P be an off-prime number. Then a Dehn P coloring of D is a map from the set of regions of D to ZP, satisfying this condition. So this condition means the colors of both regions for over arc. So adjacent regions for over arc, the sum of the colors are unique. So more precisely, so when we see the sum of the colors are for these adjacent regions, the sum is A1 plus A3. And so this is same work. So when we see the sum from this point, the sum is A2 plus A4. So this condition means that the value should be the same. Okay. And crossing of DC, this is our Dehn color diagram. DC is trivially colored if the colors and the diagonal, the colors of the regions in the diagonal position are the same. So for this crossing, A1 equals A4 and A2 is equal to A3. So for this case, this crossing is trivially colored. So then P coloring C of D is trivial if all the crossings of DC is trivially colored. So actually there are two types of trivial coloring. So one is monochromatic coloring, so with one color. And the other one is checkerboard coloring, like this. And node K is then P colorable if there exists a non-trivially then P color diagram of K. And we denote by color P and T of D the set of non-trivial then P colorings of D. So this NT means non-trivial. And actually there exists a correspondence between Fox colorings and Dehn colorings. So, so correspondence is given like this. So when we have the Dehn coloring, by taking the sum and give the sum to the semi-arc, like this, we have Fox P coloring. So, and when we had non-trivial Dehn coloring here, the corresponding Fox coloring is also non-trivial. So we can see that K is Fox P colorable if and only if K is Dehn P colorable. And let K be a Dehn P colorable nodes. The minimum number of Dehn P colors of K is denoted like this. And this is defined by the minimum number of distinct colors of ZP, which gives our non-trivially Dehn P color diagrams of K. So as mentioned here, Dehn colorings is the region coloring version of Fox colorings. So Dehn colorings are corresponding to Fox coloring. So we also would like to know the minimum numbers of Dehn P colors for nodes. So these are the natural question. How can we evaluate the minimum number of Dehn P colors of nodes? And does there exist two nodes which are distinguished by using minimum numbers of Dehn P colorings? Dehn P colors. And next section, I'd like to show result on minimum numbers of Dehn P colors we obtained. So when P is equal to 3, minimum numbers of Dehn 3 colors of any node K is equal to 3. So yeah, this property is shown very easily. So and when P is equal to 5, the minimum number of the 5 colors for any node is equal to 4, always equal to 4. So this can be shown by deforming non-trivially Dehn 5-color diagrams and omit one color. And theorem 1, for any Dehn p-colorable node K, the minimum number of Dehn p-colors of K is greater than or equal to this is for a function of log 2p plus 2. So yeah, this property is the same as the property when Fox coloring as in the case of Fox colorings. So theorem 2, when p is an odd prime number less than 2 to the 5th power, there exists a non-trivially Dehn p-colored diagrams DC such that if the number of colors is equal to this lower bound, so the flow function of log 2p plus 2, then the set of colors are affine equivalent to these sets. So this theorem means we can obtain the candidate of colors which might give non-trivial Dehn p-color diagrams. So theorem 3, for any odd prime number less than 2 to the 5th power, and except for 13 and 29, there exists the Dehn p-colorable node K, satisfying the minimum number of Dehn p-colors of K is equal to this lower bound. So for a function of log 2p plus 2. So what about the case of 13 and 29? So theorem 4, when p is equal to 13 or 29, for any Dehn p-colorable node K, the minimum number of Dehn p-colors of K is greater than or equal to the flow function of the log 2p plus 3. And the theorem 5, for any prime number greater than 5, less than 2 to the 5, except for 17, there exists the Dehn p-colorable node K, satisfying this condition. So minimum number of Dehn p-colors of K is greater than or equal to the flow function of log 2p plus 3. So from theorem 4 and theorem 5, we can see that this log 2p, for a function of log 2p plus 2 is not possible for some p. And from the theorem 3 and theorem 5, we can see this. So there exist 2 nodes which can be distinguished by using minimum number of Dehn p-colors for some p. So these properties are different from the case of Fox colorings so far. So next, I'd like to explain about cocycle invariant. So first, when we had ZP and these some maps, we can define symmetric local biquandle homology groups and homology groups. As the time is limited, So I'd like to skip to explain about this homology groups and cohomology groups. But we have this as a cocycle, two cocycle. So the homomorphism therapy from this chain group to the ZP defined like this is two cocycle. Okay. This is actually coming from the Mochizuki three cocycle of dihedral bundles. So corresponding to Mochizuki's three cocycle. Let this see the Dehn colorage diagram. Then we can obtain the weight from each crossing. So like this. So when we have the crossing, we choose one region from the 4 regions around the crossing. So I chose this crossing. So in this case, this crossing with this star, and we name this region X1, and we name this region X2. So this region means this region is adjacent to X1 by this under arc. And we name this region X3 and this region X3. So this region is adjacent to X1 by this over arc. Then the weight is the sign and the curve CX1 and the curve X2 and the curve X1 and the curve X3. And sign is given like this. So the pair of the normal orientation from X1 to X3 and the normal orientation from X1 to X2 is corresponding to same at the right hand orientation of R2, then the sign is plus. Otherwise, sign is minus. And we denote by WDC the sum of the weight, all of the crossings. Then we can see this property. The sum of the weight is in the kernel of the boundary map of this this homology chain complexes. And we have next theorem. The Marot set which is denoted by phi theta b and t of d. So this is okay. The element is theta p of WDC for all of the non-trivial coloring, non-trivial Dehn colorings of D. This Marot set is invariant of unoriented nodes. So this invariant is called cocycle invariant or symmetric local biquandle cocycle invariance. So in this talk, I just say cocycle invariance. So let's see this example. Let P let's see the case when P is equal to 7. And this is our Dehn 7 color diagram, non-trivially colored. And from this crossing, so we choose this region, then the sign is plus, and we have plus 0, 0, and 0, 1. Like this, we can obtain this weight. From this crossing, we choose this region, then sign is minus, and the weight is minus 0, 1, 0, 2, like this. So like this, we can obtain the sum of the weight. And we send this weight sum by theta 7. This theta 7 is 2 cocycle I showed. So this is yeah coming from Mochizuki 3 cocycle. So by calculating this value, we have, or this is equal to 5. So like this, for all of the non-trivial than 7 colorings for this diagram, by calculating this value, we have the cocycle invariance. So next, let's see proofs of main result. So first, let's see this theorem 4. So when p is equal to 13 or 29 for any DMP color of node k, the minimum number of DMP colors of k is greater than or equal to the floor function of log 2p plus 3. So I'll show this theorem when p is equal to 13. Okay. So let this be a non-trivial DMP 13 color diagram of k. Assume that the number of colors used for this color diagram is equal to equal to from a function of log 213 plus 2, which is equal to 5. So by theorem 2, so theorem 2 gives the candidate of colors. So by using theorem 2, we may assume that the colors are 0, 1, 2, 4, 7. So, so by using these 5 colors, we have the weight sum is written like this. So, and the boundary map of this weight sum should be 0. By calculating this value, we have this equality. So especially we can see that so the relations from these coefficients, we can see that T1 equals T2 equals T3 equals T4 equals 0. And T4 equals 0 means that T4 is this coefficient. T4 equals 0 means the number of positive crossings colored by 1474 is equal to the number of negative sign of crossing colored by 1474. So if we have a crossing colored by 1474, so for semi-arcs with the color 1,4 for this both sides, and the semi-arc with the colors 7,4 become one component. So yeah, because the other arcs we cannot combine for the other arcs. But so this and the other arcs form the other components. So this contradicts that D is a knot diagram. So yeah, so next, if there exists a crossing colored by 0717, and we don't have the crossing 1474, the same situation happened. So this contradicts that the K is a knot. So by repeating this discussion, we have the conclusion. We have the conclusion. So there does exist the starting color diagram DC satisfying the number of colors is equal to the floor function of log 2 13 plus 2. Okay. So next, let's see theorem 7. So this is new theorem. Okay, let P be an operand number with P is greater than 5 and less than 2 to the 5th power, and the P is not equal to 17. Let K be then P colorable or not. If this cocycle invariant doesn't include 0, then the minimum number of then P colors of K is greater than or equal to the plural number of log 2P plus 3. So I'd like to show this property when P is equal to 7. Okay, let DC be a non-trivial then P color diagram of K. Assume that the number of colors is equal to the this for a number of the log to 7 plus 2, which is equal to 4. So by using the theorem 2, so this gives a candidate of colors. We may assume that the colors are 0, 1, 2, 4. So then by using the 4 colors, 0, 1, 2, 4, we have this non-trivial color crossings. So 9 types of crossings. And then we can write the weight like this by using 4 colors for some coefficient. So since the sum of the weight is the element of the kernel of the boundary map, so the boundary map of WBC should be equal to 0. So by calculating this value, we have this equality. So from the relations obtained from this coefficient, we have this congruent expression and this equality. So by applying these relations for this WDC and sending this WDC by theta 7 to cocycle theta 7, we have this value is equal to 0. So this contradicts that the cocycle invariant doesn't include 0. So this assumption contradicts this assumption. So thus, the number of colors should be greater than or equal to the floor function of log 2 7 plus 3. And consequently, so for nodes K, the minimum number of then 7 colors of K is greater than or equal to the floor function of log 2 7 plus 3. So next, let's see theorem 5. Theorem 5 is for any prime number P greater than 5 or less than 2 to the 5th power, except for 17, there exists then P colorable node K satisfying this condition. So minimum number of then P colors of K is greater than or equal to the floor function of log 2P plus 3. So for this proof, we may give some examples satisfying this condition. So in the case the p is equal to 7. So yeah, this diagram, this node satisfies this condition. So let's see. Let K be the node represented by this diagram. And then by calculation, so the cocycle invariant become like this. So this cocycle invariant doesn't include 0. So by the previous theorem, we have the minimum number of 7 colors of the node K is greater than or equal to the floor function of log to 7 plus 3, so which is equal to 5. And since this color diagram is colored with 5 colors, 0, 1, 2, 3, 5. So we can also say that the minimum number of 7 colors of this node K is less than or equal to the for a function of log to 7 plus 3. Therefore, we can say that minimum number of Dehn 7 colors of this node is equal to 5. Okay. So next, let's see, theorem 3. Theorem 3 is for any prime number p less than 2 to the 5, except for 13 and 29, there exists then p colorable node K satisfying this equality. So minimum number of Dehn colors of K is equal to the floor function of log 2p plus 2. So we may also give some example satisfying this equality. So when p is equal to 7, let k prime be the node, which is represented by this diagram. Okay, then this minimum number. This diagram is colored, then 7 colored using 4 colors, 0, 1, 2, 4. So, so this means a minimum number of then 7 colors of K prime is equal to the floor function of log 2, 7 plus 2. So this is equal to 4. So let's record this question. So do there exist 2 nodes which can be distinguished by minimum numbers of them big colors? So answer is partially yes, because so this case yeah, the this for this node, the minimum number of Dehn 7 colors is equal to 5. And this case, this node, minimum number of Dehn 7 colors of K prime is equal to 4. So they are distinguished by using minimum number of Dehn 7 colors. And finally, okay, I'd like to show the case when p is equal to 17. So I showed the theorem 7. So theorem 7 is let p be a prime number with the p is greater than 5 and less than 2 to the 5, and p is not equal to 7. Sorry, p is not equal to 17. So what happens when P is equal to 17? So actually, when P is equal to 17, there exist nodes satisfying this assumption, but doesn't satisfy our this assumption, but this doesn't satisfy the conclusion. Okay, this is such case. So yeah, when we calculate the cocycle invariant for this node, we can see that this cocycle doesn't include 0, but this is colored by 0, 1, 2, 4, 5, 9. So 6 colors. So this is this is colored by using floor function of log 217 plus 2. So this case doesn't satisfy this condition, this conclusion. So this is all. Thank you very much.